Let's do one more example of using shortcuts to find the residues of functions at poles. One of the problems on your homework 6 was to find the residues of the function 1 over z to the 4th plus 1 at each of its poles in the upper half plane. So the first thing to do here is simply to find what the poles are in the upper half plane. So we need to find the places where the denominator is 0. So let's take z to the 4th plus 1 and set it equal to 0. That's the same as z to the 4th equals negative 1. And you learned on an earlier homework assignment how to find the solutions for this in the complex plane. And you might remember that there were 4 of them. In pictures, all 4 solutions lie on the unit circle, and they're symmetrically placed. The solution in the first quadrant was e to the pi over 4 times I. In the second quadrant, we had e to the 3 pi over 4 times I. In the third quadrant, e to the 5 pi over 4 times I. And in the fourth quadrant, e to the 7 pi over 4 times I. Now in this problem, we're only interested in the poles in the upper half plane. So that means we're going to be looking at z2 and z1. Now in this video, I'm just going to find the residue at z2. I'm going to leave z1 to you. So a little bit later in the problem, we might want to write down an explicit expression for this one. Using Euler's formula, remember that e to the I theta is cosine theta plus I sine theta. So z2 is the same as cosine of 3 pi over 4 plus I times sine of 3 pi over 4, which is the same as negative square root of 2 over 2 plus square root of 2 over 2i. So we'll keep that in mind for later calculations. So for now, since we have a simple pole at each one of these z's, we get to use this formula for finding residues. So the residue of this function, f of z, at z2 is going to be the limit as z goes to z2 of z minus z2 over z to the 4th plus 1. Now remember, if I plug any of these in, I'm going to get a 0 in the denominator. And notice if I plug z2 in, I also get a 0 in the numerator. Now there are a couple of ways to proceed. One possibility would be to factor the numerator and denominator. So in the numerator, it's already factored. In the denominator, since I know the 4 solutions, the 4 zeros, I know that the denominator factors is z minus z1 times z minus z2 times z minus z3 times z minus z4. And then I could cancel the z minus z2s and then substitute z2 in for each of these z's and simplify. Unfortunately, that kind of makes for a big algebraic mess. So let me show you a cleverer way of doing it. As I mentioned before, if I use direct substitution, I get 0 over 0. So that means that this is a candidate for L'Hopital's rule. So this will be the same as the limit as z goes to z2 of the derivative of the numerator over the derivative of the denominator. The derivative of the numerator is 1, and the derivative of the denominator is 4z cubed. And now I can use direct substitution. So this is the limit, I'm using direct substitution. So I get 1 over 4z sub 2 cubed. Now once again, if I want to, I can substitute in e to the 3 pi over 4i for this and start simplifying. There's another algebraic trick I can do here. And that's going to be to multiply top and bottom by z2. That gives me z2 over 4 z2 to the 4th. But remember, at each of these 4 solutions, z to the 4th equals negative 1. So down here where I have z2 to the fourth, I can replace that with a negative 1. So I have z2 over negative 4. So that's negative 1/4 times z2. And over here we wrote an expression for z2. It's negative square root of 2 over 2 plus square root of 2 over 2i. So that means that we get the square root of 2 over 8 minus square root of 2 over 8 times I. And that's the residue at z2. If you go through similar steps, you can get the residue at z1. And actually in the problem in your homework, I asked you to add those two residues together. And when I show you the residue theorem in our next video, you'll see why we do that.